Back at it again for Physics 142 Online. Before doing an example problem involving the resolution of two distant sources, I first want to do a quick review of the condition for resolution. Remember that the limitation on resolution of two objects is caused by, among other things, the diffraction of the light that comes from those objects as it passes through, for example, the aperture of your eye, the pupil. This would also apply to the use of a telescope or binoculars or some other kind of viewing device. And so the reason we see limitations in resolution is illustrated on this slide, which I showed in class. If two objects in the lower panel are very close together, and we think of these as two sources of light, then the light that comes from the two sources, when it forms the single slit diffraction pattern, which would then be on the retina of your eye or on the film of a recording device that's used to capture an image, those diffraction patterns would overlap to such an extent that there would just appear to be one smeared out pattern and one object. Probably pretty fuzzy. Then on the other extreme, when the two objects are far apart, relatively speaking, the two central maximum peaks for their diffraction patterns appear well separated, and they're not merged together. We clearly would see a bright spot for one, and then a minimum in light intensity in between, and then a bright spot for the other one. When objects are just barely resolved, and this is the Rayleigh criterion that we'll talk about in just a minute, we can see a peak and then a bit of a dip in the light intensity, and then another peak for the second object, and we can just barely make out that these are distinct objects. And so what this might look like visually is illustrated in these slides that show on the top two well-resolved objects. Clearly you can see that there are two diffraction patterns that are overlapping. The middle one, it's elongated to such an extent that we can tell these probably came from two different objects, but they're close enough together that the diffraction patterns are overlapping. And then the bottom one, we have two objects that are so close together they appear to just show one diffraction pattern. So the Rayleigh criterion is somewhat arbitrary, but it's a good rule of thumb to use for when we will be able to just barely resolve two sources as actually being two sources. We'll recognize as we look at these that the light comes from two different sources. And the criterion is simple. Objects can just barely be resolved when the central maximum of one object, and here look at S2 in this plot, the central maximum for S2, the upper peak, falls at the first minimum in the diffraction pattern of the other one. And so S1 has a diffraction pattern that's centered right here where the arrow says maximum, and its first minimum, indicated by the blue line, falls at the same place as the central maximum for S2. And as a result, once again, when those two patterns superimpose, we see two peaks with just a bit of a dip in light intensity in between. So that's the Rayleigh criterion. And a very little bit of mathematics can be used to determine the condition for the angle of separation. What we're finding is the minimum angle of separation that's required to resolve two objects as separate objects. So first we just look at the criterion for the location of the first minimum, and we see that that's from a sine theta equals n lambda. That's sine theta is lambda over a. We obtained that by plugging in n equals 1 for the first minimum. And usually when we're talking about questions of resolution, the sources or the objects are far away from us. And so the small angle approximation is going to be a very good one. Typically these angles will be very, very small. So sine theta is approximately equal to theta, and that gives us this simple criterion for the minimum angle of resolution. And in the case of a circular aperture, you see the upper boxed equation is for a rectangular aperture, because that's where the original formula came from for the location of the minima in the diffraction pattern. When we deal with a circular aperture like your pupil or like the lens on a camera, the geometry is such that there's a numerical factor that gets introduced, and instead of the slit width, we're dealing with the diameter of the aperture. And so we won't derive this, but just use this as what we call then the Rayleigh criterion. for circular apertures. And what I'd like to do is just stress and ask you to think about what this theta minimum means. Usually what we're talking about is a situation where there are two sources and their position is fixed, so that depending on where you are, if you're very close to those sources, then you would see a larger angle of separation. The further away you get from those sources, you would see a smaller angle of separation, and at some point you would get far enough away where you would lose the ability to resolve the sources. Alternatively, if you start off very far away and move closer and closer, the angle of separation will get bigger and bigger, and then when it finally reaches the minimum needed for resolution, you will be able to see them as two separate objects. So think about this equation. If d is large, then theta min is small. And what that means is if theta min is small, that means you can be far away and still resolve those objects. Because as you get far away, the angle of separation is small, right? So if theta min is small, it makes the objects easier to resolve. If d is small, which makes theta min in this equation large, then that makes the objects harder to resolve, right? If the minimum separation angle is large, that means you have to get really close in order to see them as separate objects. So think about that, and in just a moment I'll do an example that will illustrate how to put numbers in these equations and come up with meaningful answers. Let me give a tangible illustration for a problem that's similar to the one I'm going to work out in just a moment, and that is resolving the headlights of an oncoming car. So we see on the far left-hand side the headlights on the car when we, on the right-hand side with this sketch of your eye, are looking at them. And so you can see that the angle of separation varies with the distance. If the headlights on the car, if the car is getting closer, the separation of the headlights is staying the same, but the angle of separation that you measure as the viewer gets larger. So when they're far apart, we can see that the angle is smaller than the minimum angle needed for resolution. And here is the Rayleigh criterion for a circular aperture. Theta min is 1.22 lambda over the diameter of the aperture. So if the separation angle, which solely depends on the geometry, how far apart the headlights are, and then what the distance is from the headlights to you, if that angle is smaller than the minimum angle needed, you can't resolve them. When they get close enough that the angle of separation is exactly equal to the Rayleigh criterion angle, the minimum that's needed for resolution, then you can just barely resolve them, and you'll probably begin to see that this is an automobile and not a motorcycle coming toward you. And then when they get even closer still, you can see that the angle is greater. And so the practical part of the criterion is that the separation angle, in order for resolution to take place, the separation angle of the two sources of light has to be greater than or equal to the minimum angle specified by the Rayleigh criterion. And now it's time to do an example problem for just this situation. Okay, let's consider a practical sort of problem that I've referred to in class, and that is being able to resolve the headlights of a car at night as separate objects. So if you see a light in the distance coming towards you and you're on the road, how soon will you know, or at what distance can you tell whether it's a motorcycle or an automobile with two headlights? So here's the question. The headlights are approximately 1.5 meters apart, and assuming that your pupil has a diameter of 4 millimeters, what's the maximum distance at which you can resolve the headlights of the car? So we are using Rayleigh's criterion in doing this. And it's a fairly straightforward application. So let's draw a picture. Always have to draw a picture first. We've got now the two headlights over here, and then at some distance away we'll just draw a little image for the pupil of your eye, and then to indicate the angle which is mentioned in the Rayleigh formula, I want to draw lines going from each of the two sources to the aperture of the pupil, and then define the angle of separation of these two sources. Okay, so right there we've got, and I'll draw in a horizontal line that goes right down the middle of that angle. We'll put in a symbol Y to represent the separation of the sources, separation between the headlights, and of course we know that the pupil has a diameter D, which is given to us as 4 millimeters. The separation distance is 1.5 meters. So the actual angle of separation between the two objects relative to where you are as the observer, as the pupil, right here, is theta. That's the entire angle of separation between the headlights. And one other thing, we should put in here the quantity that we're actually trying to find, which is the maximum distance, L, at which you can be away from the headlights and still resolve them as separate sources. So there's something very straightforward that we can do. We can see that this Y is actually the entire distance, and if we were to look at half the distance of that, Y over 2, that would be the vertical section of a right triangle that we could make right there. And so from some very simple trigonometry, right, tan theta, actually tan theta over 2, because if we take half the angle theta, then half that angle, the tangent of that would be half of Y divided by L. So we get Y over 2 divided by L. And as usual in these kinds of problems, we assume that you are really far away from these two objects because you're trying to find the maximum distance at which you can resolve them. So we'll take the tangent of the angle as being approximately the same as the angle itself. So tan theta over 2 is approximately theta over 2, and then we can just solve for theta very easily and say that theta is approximately Y over L, having made the small angle approximation. And one thing that's important is when we make the small angle approximation, that assumes that the angles that we're talking about are in radians. So when we calculate the value for theta, as we're going to do in just a minute, it has to be in radians. So let's go ahead and do it. We'll write down, well, theta is just, well, we don't know what L is, right? We don't know exactly what the L is. We're going to try to find that out. So theta is Y over L. Now, the Rayleigh condition comes in when we ask what is the minimum separation, angular separation, between those objects at which we can just barely resolve them. And so the formula for a circular aperture says theta min is equal to 1.22 times the wavelength over the diameter. Oh, and one thing, now that the wavelength is in play here, usually in problems like this where the light is actually not a single wavelength but comes from across the entire visible spectrum of wavelengths, we're going to assume a value to use for the wavelength that will be representative of all the visible wavelengths. And it turns out that the visible spectrum runs approximately from 400 to 700 nanometers. And so smack in the middle of that range is 550 nanometers. So sometimes the problem will say that. This one did not. So we will assume lambda of 550 nanometers, and we'll get an answer that will be approximately correct for the midpoint of the visible spectrum. Okay? So lambda, theta minimum, we now can calculate that because with our assumption about the wavelength. So theta min is 1.22 times 550 times 10 to the minus 9 meters, that's a nanometer, right, 10 to the minus 9 meters, over the diameter, which is 4 millimeters, or 4 times 10 to the minus 3 meters. So when we do this, 1.68 times 10 to the minus 4 radians. Remember, these formulas, the Rayleigh formula as well as the formula that I worked out from the geometry of the situation, both have theta in radians. So that's the minimum. Now what does it mean? Let's just think for a minute about what this means. This means that the condition for resolution for any given distance L and separation y, the condition for resolution is that theta has to be greater than theta min, which is why we call the Rayleigh condition the theta minimum, right? If the actual angle of separation is greater than the Rayleigh angle, then we can resolve the two objects. And I guess I'll put in greater than or equal to because the Rayleigh condition is written as the minimum value. If, on the other hand, theta, the actual angle of separation, is less than what the Rayleigh condition says is the minimum, we cannot resolve. Okay? So that's what we want to do. We want to set the expression for the actual angle of separation equal to the minimum angle and then solve for L. So let me just do that. Set theta, which is y over L, equal to theta min, and then solve for L. That's pretty easy to do at this point. So we got y over L is equal to 1.68 times 10 to the minus 4 radians. Solving for L gives L equals, of course, just y divided by 1.68. So I'll do the final calculation right here. 1.5 meters, that's what y is, divided by 1.68 times 10 to the minus 4 radians, and the L value that we get is really quite large. It's 8,940 meters. So what this means, actually, since we found the minimum angle, then this turns out to be the maximum L, right? So I'll call it L max. It's the furthest distance we can be and resolve those as separate objects. Now, one thing I should say about this, though, is this is representing an ideal situation, an ideal case. If this whole experiment were taking place in the vacuum or near vacuum of outer space, then it would probably be a pretty good approximation to what you would see. However, on Earth, the light that goes from the headlights to our eyes has to pass through the atmosphere. And the atmosphere is made up of lots of molecules of oxygen and nitrogen, and perhaps a little bit of smoke and haze of different kinds, water droplets, and so there's lots of light scattering that happens on the way from the sources to your pupil, and that further diminishes your ability to resolve these things. So what we calculate with the Rayleigh criterion is what we call the diffraction limit of your ability to resolve. But in reality, if you did this experiment, as I've tried to do several times on a country road at night, and figure out by counting the time how far a car can be for me to resolve the headlights, you would find the answer to be significantly less than this. And so this is really an ideal case, and L is actually less due to, as I've said, atmospheric scattering of light. So if that answer seemed a little bit big to you, then you're right. It is a little bit too big. Nevertheless, this illustrates the maximum ability that we would have under ideal conditions to resolve these two sources as separate objects at a certain distance, solely because of our pupil and the diffraction that goes on when the light passes through the pupil and then forms an image on the retina. I hope this helps understand a little bit more about how to use Rayleigh's criterion.